Hello everyone, welcome back to Risha's Education, and today we'll be solving some questions from Joseph Gallian series that we were doing, and in this video we are going to solve from question number 46 to 50. This will be our second last video of chapter 2, and for the rest of the video you can go to and check out our playlist. Now let's start with the 46 number question. So we have Okay. So we have proved that the set of 3 cross 3 real entries in of the form, we have given one form and this is a group. So we have to show that this is a group. Now, if you say about closure property, I would like to say that we have multiplication defined in these ways. Okay, so we have 2 entries and we have multiplications defined already, means 1ab is multiplied with this is multiplied with this, and so on. It's there. It's simply a matrix multiplication. I have to see that whether this also belongs to same category. Here A, B and C are belonging to real number. Okay, real entries, right? So what it's just a group of some matrices from, you can say, MNR. Yeah, and then if you see that if A and A dash belongs to real number, A plus A dash also belongs to real number. This also belongs to real number and this also belongs to real number. So in total, this matrix is also the form of this matrix only. And hence, you can say that the closure law is satisfied. So closure property is satisfied. Okay. Next comes associativity. Now this types of matrix is a subset of MNR. And MNR do follow associativity. So this also follow associativity, because if this does not follow associative property, then what happens? MNR will be in contradicting that it is associative. Okay. Next comes the identity property. What happens to the identity element? So identity for the matrix is always 1 0 0 0 1 0 0 0 1. In terms of multiplication, in addition, we have 0 matrix only. And if you see that here A is equals to B is equals to C and this is equals to 0. And also this matrix belongs to the same category of matrix. Now what happens? I have to find the inverse. Inverse is only thing that we need to see a little bit. So similarly, for the inverse, if you find, suppose I take A is equals to 1AB, 0, 1C and 0, 0, 1. Then similar way, like we find inverse for any normal 3 cross 3 matrix, we will go like that only, and we will see that the inverse that we will get is of the form A1, and we have minus A, and then we will have, so this will be AC minus B, and this will be 0, 1. Here we have minus C, we have 0, 0 and 1. The determinant will come 1 here also. So we need not to divide by any of the number. And yes, we also find for every matrix we have a determinant, because these also belongs to real number only, and this is the same type of matrix. And hence we can see that the set of matrices which we have given forms a group under multiplication. Okay. So next move on to the question number 47. We have that if G is a group with the properties that square of every element is the identity, then G is abelian. You should keep this like a property in your mind, and this will help you in solving many questions. Whenever you want to show, whenever you get this, you will clearly say that this is abelian and something like that. So we have to show this, like whenever this is true and G is abelian. So let A and B belongs to G. Okay. Then by the given property, what do we have? We have A square is equals to identity. We have B square is equals to identity. Also, when A and B belonging to G, we have AB belongs to G by the closure property. So when AB belongs to G, what do we have? We have AB whole square is equals to identity. Also, what do you think about A square into B square? It's identity times identity, which is equals to identity. Now from here and here, what you can get is AB whole square is equals to A square B square. So what you can write is AB is equals to A, B, B. Okay. By the cancellation law, you have BA is equals to AB. We can cancel A by the left and we can cancel B by the right. So we have AB equals to BA, and this implies that G is abelian. Okay. Next, move on to the question number 48. We have a finite group. We want to show that the number of non-identity elements that satisfy the equation x to the power 5 is equals to identity is a multiple of 5. I would like to first of all make a correct statement. The statement that is given to you here, that is 5, must be replaced by 4. So here you should have 4 elements. Okay. So let's start solving this. So we have, suppose X belongs to the set S, where we have non-identity elements having this property. Okay. So X belongs to S and we have x to the power 5 is equals to identity. So my claim is x square, x cube and x to the power 4 also belongs to S. Why? Because you can see that x squared to the power 5 is equals to x to the power 5 to square is also identity, and x cubed to the power 5 is also identity in the similar way, and x to the power 4 to the power 5 is also identity in this similar way. Now what happens, I have to show that x square, x cube, x power 4 are distinct. How will I show this? Suppose I have x to the power I equals to x to the power j. Suppose this happens. What will be I? It will be either 1, let's say I is less than j, and this will go up to 4. Okay, this can be equal to 4. So from here, I can say that x to the power I minus j is equals to identity. Now, I would claim I minus j is in between 1 to 3. Why? Because if I say the maximum one, j is equals to 4 and I is equals to 1, then only the difference is 3, and hence we have so we have maximum of 3 here. Now what happens? I would like to say that I minus j is not equals to 1. Why this is? Because then x will be equals to identity. But we have considered that x is non-identity element. So x is I minus j is not equals to 1. Okay. Then what can be I minus j? So I minus j can be 2 or it can be 3. Now when I minus j is 2, what you can do is x to the power 2 or x to the power 3. I can multiply by 3 or multiply by 2. So this will give me x to the power 6 as identity. Why? Because x to the power I minus j is identity. So if I minus j is 2, I will multiply with 3 both the side. And if it is 3, I will multiply with 2 both the side, means squaring both the side. We get x to the power 6 equals to identity. But we know that x to the power 5 is identity. So we have x is equals to identity, which is a contradiction. Why? Because we have considered that x is not equals to identity. Hence, what we can say? We can say that all the xi and xj are distinct. And this is what was required here. Now we have the question, if the stipulation that the group be finite is omitted, what can you say about the number of non-identity elements satisfying this? So if we have infinite order element, if we have infinite group, then we can have two possibility. Okay, so suppose G is infinite. Now I have two possibility. G can be of the form, say, suppose I take personally as Z. Then if you notice, then order 5, or you can say that x to the power 5 equals to identity, satisfying non-identity element is 0. Why? Because every element in Z except 0 have order infinite. Okay, clear this thing? Because what happens, if you have 0, then 0's order is 1, and else everything has infinite order. Why? Because, yeah, so we have 0 order. We have only one element that's satisfied. We do not have any element, or we have just one element that satisfies this property, is identity itself. Else we don't have any element. But suppose we have similar type of group as Z5 cross Z5 cross Z5, and this is going on and on and on. Then what we can say, we have infinite number elements, infinite non-identity elements basically, with satisfied x to the power 5 is equals to identity, because we get 4 elements here, 4 elements here, 4 elements here, and it's going on. So 4 cross 4 cross 4 and so on. So I hope this is clear. Next, move on to the 49 number question. So we have list the 6 elements of GL to Z2. Okay, means ZL to Z2 basically represents only one thing, that is the order, the determinant should not be 0. Okay, so we start listing it. We first of all get 1 1 0 0 because its determinant is 1. So we have to take all those elements whose determinant is non-zero. If you see, this also have determinant -1. Again, if you see, you have 1 0 1 1. You just have to find. So we have 6 elements. So we will be finding all the 6 elements. Okay, what I am doing, I am simply putting 3 1 and 1 0, and this will have the combination of total 4 matrices. That is what I am writing here now. And the last element will be the inverse, not inverse, the identity element reverse, means 0 here, 1 here, 1 here, and 0, because it has -1 as the determinant, and consider this as S. Okay, now we have to show that this group is non-abelian by finding 2 elements. Okay, so if we find 2 elements, suppose I take the 2 element as this one, 1 1 0 1, and the second element as 1 0 1 1. Then if you will see the product as 2 1 1 1. But if you do the multiplication in the reverse order, like 1 0 1 1 and 1 0 1 1, then you have 1 0, sorry, here it will be 1 0 1. Okay, so this is how you get that these are not equal. That means they do not commute. So last but not the least, we have 50th question. Like, we have to prove the assertion that was given as, suppose we have this set. Suppose I name this set as H, 1 2 up to n minus 1. This is a group under multiplication modulo n if and only if n is prime. So what I will do, I will first consider H be a group under multiplication modulo n. So this is the symbol I am using for multiplication modulo n. And now I have to show that n is prime. Okay, we have to show that n is prime. So suppose n is not prime. So if n is not prime, then what can you say? That means n can be written in the form of AB, where 1 is less than A is less than n, and 1 is less than B and less than n. Then what happens if you see, then AB is congruent to 0 mod n. This you can say, right? So AB is totally divisible by n. So AB is congruent to 0 mod n. And from here, we should have 0 belongs to H by closure property. But what do we have? 0 does not belongs to H. So we arrive at contradiction. So from here, I can say that n must be prime. So this is the first part of the question. Now, moving on to the second part, consider, so conversely, we have to prove. So conversely, we are considering n is a prime number. Now we have to show that H is a group. So closure is quite satisfied because n is prime, then every number is co-prime to n. And then when we multiply two number, we have something remainder. And that is how we can say the closure is satisfied. Associativity is also satisfied. Only thing we need to check is the inverse because identity will be 1 in multiplication modulo n. So for inverse, consider A belongs to H. We have to find for the every random element. So I'm considering A belongs to H. We know that GCD of A and N is equals to 1. By the property of basic number theory or basic theory, if you have even read the preliminaries, you can say that there exist X and Y such that AX plus NY, so X and Y will be integers, which gives you 1. Then what you can say is AX is equals to 1 minus NY. Okay. Now, what you can write from here is AX is congruent to 1 mod N. Why? Because this will yield you 0 as remainder and this will give you 1 as remainder. So we are writing AX is congruent to 1 mod N. So for every A, we are having X such that this is happening. Okay. From here, you can say that every element of H has an inverse. Okay. So every element has an inverse. Okay, and this is how we came to the end of the video. I hope you understand it clearly. This was requiring some basic analysis and basic understanding of the concept. So thanks for watching. If you like the video, please share with your